Welcome back to the next part of our Pore Lab lecture series. Our speaker today is Martin Blunt, who is a multiple award-winning professor at the Imperial College in London, where he's chair of the petroleum engineering at the Department of Earth Science and Engineering. His research interests are multiphase flow and porous media with many different applications, including oil and gas recovery, geological carbon storage, and contaminant transport and cleaning up in polluted aquifers. He's doing experimental, theoretical, and numerical research into many aspects of flow and transport in porous system. And today he's going to provide an overview of the current revolution of the understanding of flow, transport, and reaction processes in porous media, enabled by 3D imaging from the nanometer scale upwards, microfluidics, and improved numerical methods. He will illustrate his talk with examples of work done at the Imperial College on multiphase flow in rocks to carbon dioxide storage and oil recovery. I would give the word to you. Thanks for coming and enjoy the presentation. Yeah.
Hey, well, thank you very much for that introduction. I'm absolutely delighted to have the opportunity to give this seminar. As you can see, maybe from the background, I am in my office, but actually it's my first day back for 7 months. But having picked up my mail, I have been flicking through the Pore Lab annual report. So very impressive. I will try and talk to you about our own modest contributions to flow and porous media. I'll start by acknowledging our research group, a really talented group of people from many corners of the world who actually have been working extremely well in lockdown. So let's just start straight away with, what do we do? So if you look here, this is a medical CT scanner, as you might see in a hospital. We use that to use X-rays to look inside rock samples that obviously can be up to a metre or so long and several centimetres in diameter. That's great, enables us to see average saturations. But as you know, right, it's Pore Lab, the main physics occurs at the pore scale, which is sort of micron level. So we can use X-rays. We take rock samples that may be somewhere between 5 and 15 millimeters in diameter. And we have an X-ray source here that is placed very close to the sample. And we can take three-dimensional micron resolution measurements of both the rock and the fluids within the pore space. And you'll notice that there's this gold jacket. What that enables us to do is to maintain high pressures and high temperatures. So we can reproduce reservoir conditions while we're undergoing a displacement experiment. And if that's not enough, the problem with these measurements is they do give you these three-dimensional images, but each image takes an hour or two to acquire, which isn't great when you want to look at a movement, a displacement process. Okay, so we can go to a synchrotron where we have a very bright X-ray source. Here is the X-rays are so bright they're ionizing the air, and there is our sample. We can get down now to a 1 second time resolution. So it's like X-ray specs, but even better than that because it's three-dimensional imaging. And don't worry, our students are carefully behind lead-lined doors to control the experiment. So what about the motivation for the work? Now, obviously with this audience, you know this, most of our work to date certainly been funded by the oil industry with applications to improve oil and gas recovery. But the other big application, and I think it's the only way in which the Western oil companies can have a license to operate in the coming decades, otherwise actually quite significantly they may find themselves closed down, is to guarantee that for every molecule of CO2 that's produced from burning their products, a molecule of CO2 goes underground. And I mean going underground, not planting trees or doing anything, but underground. So there is a huge need for carbon capture and storage. And if we look here, this is an assessment from a couple of years ago. We're looking here under various scenarios to prevent dangerous climate change of around 20 to 30 gigatons of CO2 stored per year. That's an industry that is as large, if not larger, than the current oil and gas industry. And it's absolutely essential if we're going to avoid dangerous climate change, because otherwise we will continue burning fossil fuels somewhere in the world and without dealing with that problem. But it's not the only application, and I notice you're also broadening your applications away from basically geological materials. So here is a fuel cell that's part of a low carbon economy where you react hydrogen and oxygen together to make water, but in so doing you generate electrical current, so you have electrical power. And what you need here is what's called a gas diffusion layer, a porous fibrous layer that the gas moves in, but then the water that's produced at the cathode has to be able to escape outwards, right? So you need things to be flowing in both directions. The other applications that we're beginning to explore, myriad applications in microfluidics, drugs delivery, etc., and obviously something quite topical here. Okay, we all have to have our surgical mask. So obviously we want surgical masks to be as effective as possible in trapping droplets and obviously the bacteria and viruses that those droplets contain. And again, the surgical mask is actually a series of porous layers. So in essence, if we're trying to understand multiphase flow in porous media, there are two things we're interested in. The first is trapping. What we want is we want one phase to be surrounded by the other in the wide pore spaces so that it can't flow. And basically, if we're looking at CO2 storage, put CO2 underground, we want the CO2 as a non-wetting phase to be trapped. Okay, that's good for storage. For surgical mask, it's the same thing. You want droplets to be retained within the mask and not go to you or to go to someone else. Okay. The other opposite thing you might want is you want to encourage fluid flow over a wide saturation range without the phases being retained in the pore space. The example of fuel cells, where you want the gas to move in, but you don't want the gas diffusion layer to get clogged with water, and obviously oil recovery. Right, where you want to inject water, you want the water to flow and move over a wide saturation range and displace the oil. So that is controlled by pore structure, which obviously we can image, but that's not going to be the emphasis of today's talk. Our thing has been looking at wettability. So wettability, the local distribution, contact angle. And then there is another phenomenon. We find that even when we're looking at the sort of representative slow flow rates that you see certainly in natural settings, we see the emergence of non-linear behavior. So we want to understand the dynamics as well of multiphase flow. So let's go straight in and show you what we're talking about. Here is a three-dimensional image of a piece of rock. This is an experiment where we have trapped carbon dioxide in the pore space of a limestone. Okay, so red, shown in red, is the rock. And this is just fancy image processing as we zoom around in it. Okay. Here are the ganglia of trapped carbon dioxide. The scale here, this is about 1 millimeter across. So we're looking at sub-millimeter ganglia. The different colors are just for illustrative purposes. Each discrete ganglion surrounded by water is shown in a different color. We want to understand wettability, contact angle. So what we do, here is a ganglion of carbon dioxide, and we're looking now, there's a carbon dioxide brine and rock. We want to measure the contact angle, the angle at which the two fluid phases contact the solid. So what's going to be shown in yellow here is what's called the three-phase contact line. And those lines form actually loops, okay? And those loops define where the two phases contact the solid. And we take a plane that's perpendicular to the three-phase contact line. And it's on that plane that we measure the contact angle. So the way I've shown it here is with fancy image analysis, but it's largely done manually. Here's the contact angle. If we look at this a bit more intelligently, if we have a pen here, we normally measure contact angle obviously through the, so this is your contact angle theta. We normally measure contact angle through the water. Okay, so this is water wet. The water likes the surface. The CO2 is non-wetting. We can see it trapped in the pore space. So this all makes perfect sense. So what about the dynamics? All right, beginning to actually now look inside of what happens. So here is synchrotron imaging of water displacing oil. And we've zoomed in and just looked at a piece of this. So this again is a real experiment imaged with about a 30-second time resolution. So the oil here is shown in red. The rock is sort of rendered semi-transparent and the water isn't shown actually just for simplicity. But you can see the dynamics of the process. Water can push out the oil, but it also accumulates in the narrow regions of the pore space and can fill here. That's a snap-off process. and it leaves behind this trapped oil as a ganglion, again, as a sort of ball in the pore space. Okay, and the figure on the right is, again, just fancy zooming around. It's showing the same thing. Okay, well, that's fine. We can quantify this. So here is an experiment where we've injected CO2 into the rock. The blue shows the CO2 that's connected, so that CO2 can continue to flow. So that seems like bad news. But as it flows, it's displaced by water. And what's shown here are the discrete ganglia of carbon dioxide. And here we're seeing about a third of the pore space contains this trapped CO2. So we can actually measure a trapping curve. This is what's trapped. This is how much you put in. In this particular experiment, you've got about 50% saturation, and you've got a trap saturation of around 30%. Okay, so that shows visually that when we're looking in the subsurface, as a CO2 plume moves, it's going to leave behind a trail of trapped ganglia, and that leads to secure storage. But before we go any further, let's try and put this on a bit more of a sort of rigorous footing, right? And we'll show why that's important in a few minutes. So let's define curvature. So if we have a line, a smooth line, or smooth curve, sorry, it's not a straight line, it's a curve, okay? At any point, you can have a circle that just fits, and the curvature is 1 over the radius of curvature. Okay, that's you probably know that. We're interested in multiphase flow, and so we're certainly interested in the behavior of fluid interfaces, okay? So in 3 dimensions, you actually have 2 radii of curvature, 2 principal radii of curvature in orthogonal directions, R1, R2, with their curvatures kappa 1, kappa 2. So if you've got something that's sort of like an apple, I even have a real apple here, let's assume it's a sort of sphere, then its curvatures are equal in both directions. If you have something that's more pear-shaped, right, you know, the whole point about a pear-shaped is in one cross-section, it's circular, goes round, okay, and in the other cross-section, it's sort of bulging like that. And so, in fact, the curvatures have different signs, because bulging out, we can assume as positive curvature, bulging in is negative curvature. So, very interesting. Why would we want to look at curvature? Well, the first reason is, if you know the Young-Laplace equation, curvature is proportional to capillary pressure, the pressure difference between the phases. So the interfacial tension times the total curvature will give you the capillary pressure. So that's sort of useful. But you can also define a Gaussian curvature, which is the product of those 2 curvatures. You might say, okay, well, I mean, you can define it, but so what? The reason why it's rather interesting is the Gauss-Bonnet theorem, a remarkable theorem, as Gauss called it, because what it says is the integral of the Gaussian curvature over a surface, okay, is 4 pi times the Euler characteristic, which is basically the number of objects minus the number of loops plus the number of holes. If you've just got a blob, the Euler characteristic is 1. So let's make it easy. So if you have a sphere and you integrate 1 over r squared, because that's the Gaussian curvature, over the surface, which is 4 pi r squared, you get 4 pi. So you can see it for a sphere. But if I were to take any object, right, so this apple, any object, however I distort it, as long as I don't create holes or loops, I still get the same integral of the Gaussian curvature. So what this enables you to do is to understand connectivity, because an object with many loops, good connections, so the fluid can flow in lots of different pathways, will have a negative Gaussian curvature, negative Euler characteristic, whereas something that forms lots of ball-shaped objects, so lots of things trapped in the pore space, that's going to give you a positive Gaussian curvature, poor connectivity, things are trapped, positive Euler characteristic. So here is just some classic examples. This is the work of Anna Herring and colleagues, right? So this is objects 1, loops 0, holes 0. This is with 2 objects. This is a donut, which has 1 loop. It's not actually a hole. A hole actually would be something that's completely enclosed by the shape. Okay. Okay. So now let's go back to trapping and flow, and it's an apples and pears problem. So for trapping, we pretty well know what we want. right? We want one phase to be wetting, contact angles below 90 degrees. I've shown that. And then the non-wetting phase, the other phase, is trapped in the larger pore spaces. And that leads to these ball-shaped fluid-fluid interfaces with two, and we've measured this. Actually, it turns out most places you have two equal radii of curvature. The Gaussian curvature is positive. Okay, that's all consistent with topology. But what's the opposite? What's ideal for flow? And now suddenly you get something, you can read the slides, but traditionally people say, well, if you want flow, what do you want? And people say, oh yeah, just a minute, contact angle, it's low, near zero. So you want the opposite, so you want a contact angle near 180. So for instance, a strongly oil wet rock will give you best recovery. In theory, the oil does stay connected, but in practice, the oil tends to get retained in the pore space. And we know, as reservoir engineers, actually, oil wet rocks give you the worst water flow recovery. So that's not the one. Then people said, okay, it's not the opposite. It's somewhere in between. I know. Contact angle 90 is the best. And that's not wrong. And people have shown this, you know, the recovery sort of hits a sweet spot at some intermediate wettability. But that's always been very vague, to be honest. Sort of something in between gives you the best recovery. Look at it this way. The hypothesis is what's the opposite is where the two radii of curvature are, yes, equal and opposite, right? So one R is minus the other. So apples, two positive curvatures, pears have a negative curvature. The Gaussian curvature is negative. That's going to lead to good connectivity, lots of loops in the structure. So what you want is you want a minimal surface. Minimal surface is a bit of a hot topic in mathematics. People have been thinking about them for hundreds of years. The classic minimal surface is a catenoid. If you actually have a string and you dangle the string, that's a catenary. If you were to form the surface of revolution, that's a catenoid. And it's the shape you get if you've got two soap bubbles and you have a soap film between them. That's what you get. Why do you get this? Think about it, it's fairly obvious. You've got this soap film. The pressure this side of the film is atmospheric. The pressure this side of the film is atmospheric. Therefore, there is no pressure difference across the film. Therefore, the average curvature must be zero. And it clearly has to be curved because you've got a ring here in one direction, so it has to have an equal and opposite curvature in the other direction. Okay. There's another, a helicoid is another minimal surface. Okay. When do you get minimal surfaces? You get minimal surfaces in a situation where the three-phase contact lines are pinned, that is set in place, and you minimize surface energy. So if you have a rock where nothing's actually moving, right? You may have fluid flow, but the three-phase contact lines aren't moving, then the position of equilibrium is a minimal surface, and that should ensure good connectivity. So where do we see this in rocks? Because normally you might say, well, it can't really not move because interfaces can move backwards and forwards. But in what we call the mixed wet state, so here is an example. This is a sort of corner of the pore space. Oil moves into a rock. It's there for geological time. Surface active components adhere to the solid surface. Okay. So the water is pushed out to the corners. When we inject water, we want to displace the oil. Okay, eventually some of those contacts have got to move. But most of the time, they're not moving because the water begins to move. It can even begin to bulge out, but the three-phase contact is pinned until the water's really bulging out into the oil because that's an oily surface now. So in this mixed wet state where you've altered the wettability of some surfaces, and so the water always has to sort of wait and wait and wait before it can move, you're expecting to see approximately minimal surfaces. Not exactly, because some of the interfaces have to move by definition. And then when we think about manufactured materials, you know, our fuel cells, what would you do? Well, you're not going to stuff crude oil into these fibrous layers, but these fibrous layers, you can have fibrous layers made of plastic that are naturally oil wet, or you can have fibrous layers that are made of, you know, cotton, for instance, they're naturally, or carbon, actually in this case, carbon, they're naturally water wet, and you can also coat the fibers. So what you have in a gas diffusion layer is you actually mix water wet and oil wet, or hydrophobic, not liking water, strands together. Okay. So let's test this out. Do we actually see it? Yep, is the answer. Here is a sandstone, water-wet sandstone. Here are the interfaces. They're ball-shaped. Here's the distribution of curvature. Average curvature is positive. Okay, makes sense. When we have a mixed wet system where it's been aged in crude oil, we see these rather complex interfaces. You can say they're sheet-like, but they're not flat sheets. They're crumpled sheets where there's equal and opposite curvatures. The mean curvature almost exactly zero. When the first time we saw this, we thought it must be wrong. So we did the experiment again, and we saw exactly the same behavior. So in many ways, that's sort of the main point I want to make, right? This idea about looking at curvature, connectivity, you know, and how you might design a flow process. But let's just sort of go into that in a bit more detail. First question, obviously, when I'm talking to engineers, is I say, okay, Gauss-Bonnet theorem, very elegant, Martin, but test it out. Can we? Can we actually, you know, see if that gives us good recovery? Then this does all hinge on looking at wettability. Okay, so how actually should we measure wettability? We can do it automatically from these images, but there's some problems with that because actually exactly where the three-phase contact line is, our image segmentation is most inaccurate. What about three-phase flow? I mentioned dynamic effects. What about that? And then, well, okay, let's get back to the mass and fuel cells. So first thing is, let's look at it in a real rock. This is a reservoir sample from Abu Dhabi, from producing reservoir. These are the raw images. These are segmented, oil in red, water in blue. So we start out with mainly oil. And then we do a steady state experiment. So we inject oil and water together. Okay, and the FW value here is the fractional flow. So this is 15% water, 85% oil, and we go up to 100% water. And you can see in these pictures that the sequence of steady states, we're removing most of the oil from the pore space. And this has been aged in crude oil. We've tested it out. We don't get exactly minimal surfaces, but we certainly get this negative Gaussian curvature. So you can see immediately, it looks great. But why is it good also, not just in terms of connectivity, but actually in terms of flow? Right? The water flow is quite restricted. The oil actually preferentially gets displaced. And the reason is this: the rock is a natural carbonate. It's got some microporosity that actually stays sort of full of water. I start injecting water. The water can go through the microporosity. Now what it's going to do is it's going to move out into the larger oil wet pores, because now the pores are all oil wet. The water goes into the large oil wet pores. So it does that. That's what you see. Fractional flow of 15. What I'm showing here in the different colors are blobs in the macropore space. The water is connected through the microporosity. It's not disconnected, but it fills these big blobs. So in the macropore space, it's not really connected. So its relative permeability, I'll show it next, is going to be low. Increase the water fractional flow. Those blobs get a bit bigger. They're still not connected because it's a percolation process where you're filling preferentially the big pores. Big pore, big pore, big pore, big pore, but they're not connected. And in fact, the narrow regions of the pore space are the most unfavorable, which will connect them together, most unfavorable for the water. So the water only really begins to connect at really quite a high fractional flow here at 85%. And then at 1, it does, right? It does connect. The oil can be displaced in layers. So in terms of relative permeability, we get this large region with a low water relative permeability. The oil does get confined in some of the smaller pore spaces, so its rel perm drops, and right at the end, it's confined in these layers. But in general, both phases, you know, we got this negative Gaussian curvature. There's good connectivity, low residual saturation, and the water is held back. This is actually favorable for water flood recovery. Okay, we're not saying at this point, water flood everything in the Middle East and we're going to have lots of oil. In this particular sample, we see it. In other samples, we see more classically oil wet behavior with a much higher water relative permeability and much less favorable recovery. But this particular case seems to have hit a sweet spot, and we think we understand why. Now let's look at wettability. I'm not going to say much here, but just to introduce the idea, because I think for many people in this group, you'd be interested. This is the work of Sun et al. This is Ryan Armstrong's group. We mentioned the Gauss-Bonnet theorem, haven't we? So we know, I mean, even if we do this in 2D, right, you're fairly familiar with this, the sum of the external angles of any polygon is 2 pi, right? If we have a curved shape with some angles, then it's the integral of the curvature plus the sum of the angles is 2 pi. In 3 dimensions, we've just seen it, it's 4 pi. So if we were to integrate the Gaussian curvature around here, it's going to be 4 pi plus the contribution at the 3-phase contact line, because here you've got a kink. So you've got this contact angle here that's a kink. You've got to include that plus the integral of the Gaussian curvature. That then enables us to back out the contact angle. And the reason why this is great is that actually imaging here is difficult. You've got a surface here, it's an integral over a surface. Actually, that's quite accurate. We're using fundamental concepts in topology, right? So that can't be wrong. And what's left over is related to the contact angle. So it's potentially a very powerful idea. We tested it out and it sort of works. There are some subtleties, unfortunately, but it's a really elegant way of looking at wettability using the Gauss-Bonnet theorem. The second idea is you say, okay, well, that's fine, but in your discussion, you've been talking about these pinned contacts and then only occasionally something moves. If I want a model, actually the wettability, the contact angle I want it's not what it is in equilibrium, even if I'm using a fancy topological theory. What I want to know is I want the contact angle when something actually moves, because that's what I want to put in the model. And I want things to move when it reaches that contact angle. So the way in which you deal with that is energy balance. Again, this isn't new. Norm Morrow, basically laid it out 50 years ago. So if we actually just look at the energy, and where basically there's PDV work, there's a pressure difference between the phases. We know that. Okay, there's a change in saturation. And we make that PDV work equal to the change in interfacial area. We assume there's no viscous dissipation. Then we get a relationship between changes in area, a contact angle, curvature, and again, an interfacial area. And this is the PDV work. The pressure is related to curvature, as we've already said. Okay, and the contact angle comes with a difference between the solid surface energies. So it's relatively easy to derive. The beautiful thing is, with our pore-scale images, we can now measure these things. That's the point. We can measure them. What about 3-phase flow? And also, there is a little bit of a subtlety. When we're talking about surgical masks and fuel cells, we're talking about air-water systems or gas-water, whereas with rocks, we're talking about oil water, and then we're talking about plastics that clearly are sort of oily. So let's just look at this. If we got 3-phase flow, there are 3 Young equations that we can use, right? Because they're 3 fluid pairs. Okay, so these are the 3 Young equations, relatively standard stuff. But there's rather an elegant relationship between them called the Bartter-Osterhoff relationship. And what it does is, what we do is we first of all take this one from this one. So sigma gas solid disappears. Okay, and we get this expression. And then we add it to this one. And we end up with an expression where all the solid interfacial tensions have magically disappeared. And we get a relationship between the interfacial tensions between the fluids and the contact angles. And what that means is we don't have 3 independent contact angles. The contact angle between gas and water is related to gas-oil and oil-water interfacial tensions, okay? So there's a reason why an oily surface is also hydrophobic. So an oily surface likes oil, okay? Water doesn't like it in the presence of oil, but water also doesn't like it in the presence of air. And let's go through that. Okay, so why ducks, or indeed surgeons when they're wearing a mask, aren't going to get wet is we normally have a gas-oil contact angle that's close to 0. If it's water wet, well, then we find that it's also wetting in the presence of gas. That's sort of obvious. But if it's oil wet, right, so the contact angle is 180 degrees, so cos theta is -1, then the gas-water contact angle, the cosine, is minus the oil-water interfacial tension, probably plus the gas-oil one. This number is always higher than this one, so this is negative. So here's an example. Here's a leaf, okay? The leaf has a waxy surface. The reason is that then water forms a droplet and runs off. It doesn't soak in water. Why doesn't it soak in water? It wants to soak in water in the roots. The water goes up through the plant, but you have holes in the leaves, the stoma. Those allow exchange of water vapor. It allows CO2 and oxygen to be exchanged. If it's soaked up water, actually everything would get clogged and the plant wouldn't be able to respire, it would die. On here is what I've done is I poured on olive oil. It's an oily surface, it soaks in. Okay, so an oil wet surface or something that's made out of an oil like a plastic, right? is also hydrophobic in its traditional sense, which means it doesn't like water in the presence of air. Okay, again, standard, almost intuitively obvious for every discipline except obviously the oil industry, where we have this idea that the gas always has to be the most non-wetting phase. Gas has to be non-wetting. No, it doesn't. Not in an oil wet medium. So let's have a look at this. The nice thing is this energy balance can be extended to three-phase flow. It all gets a bit more complicated, but it's a nice, elegant piece of analysis. So here's the equation. Okay, and we've tested it out. We've done some synchrotron experiments of displacement in a water-wet rock with three phases and an altered wettability rock, a rock that's been in contact with crude oil. If it's water wet, not really surprising, 1, 2 is oil water. So it's water wet, contact angle less than 90. Spreading system, so gas oil is basically 0, and the gas water is also less than 90. Fair enough. More interestingly, when the oil water contact angle is significantly above 90 degrees, in this case 130, the gas water contact angle here is also greater than 90 degrees. Okay, so it actually means that oil is wetting, gas is intermediate wet, and the water is a non-wetting phase. Okay, all of this was sort of equilibrium stuff, flow and trapping, and we measured relative permeability that assumed there's a linear relationship between flow rate and pressure gradient. But you don't always see that. So here are some experiments, actually our simplest experiments. We didn't do any fancy imaging here. We just have a piece of rock, we inject two phases together, and then we just whack up the pump rates, keeping the fractional flow the same. So what we find is, as you might expect in the textbook theory, at low capillary number, right, defined in this way, viscosity times Darcy flow rate divided by interfacial tension, you get a linear relationship. Darcy's law, no problem. But then the curves kink. And you get a nonlinear relationship with some exponent a, where a is less than 1. I know that Alex Hansen and colleagues have got an idea that maybe that exponent should be a half. We tend to find that it varies with fractional flow. If you look, those curves, those lines can cross and tend to be slightly larger than 0.5, but you definitely see a power law regime. And the threshold seems to vary with fractional flow as well. And it occurs at really very low flow rates. For those of you who know, this would be considered capillary dominated. So most people say capillary dominated, easy peasy, nothing else to say. No, even in what would be traditionally quite capillary dominated flow, we begin to see these dynamic effects. So how do we understand them? How do we understand this onset of intermittency at least? So here's a phase diagram. This is the capillary number for the non-wetting phase, the wetting phase, and this is the transition. We can predict this transition very accurately. And how do we do it? A simple energy balance. We basically say the energy from flow is converted into surface energy intermittently. That is, you create interfaces, then they destroy, create, destroy, create, destroy. That's what we see from imaging. Simple energy balance gives us when that begins to become significant at the pore scale, and it enables us to predict the behavior. We then looked in the literature because, you know, we're not the only ones to look at intermittency. And again, it's not great, but Darcy flow is basically the red points, something intermittent is blue, and our predictions look pretty good. And then just to put this in context, this intermittent flow would be seen in many natural circumstances. Okay, so we're looking here, the intermittent pathway flow that we may see with gas displacement with CO2 storage. We've also looked at this for mixed wet systems, right, where we've altered the wettability, and although we haven't got all the results put together at the moment, it still works. The theory works. We see the same intermittency. There isn't something magically different if you're mixed wet. So now let's wrap up. Okay. So what about surgical masks and fuel cells? Well, the surgical masks, if you look at them carefully, are actually several fibrous layers. And you might say, well, just a moment, they just need to be all wet, don't they? Because then that's hydrophobic. The water forms droplets, gets trapped in the pore space. So if I cough or someone coughs, it either gets repelled from the mask or it gets trapped within it. That's actually fine. The problem is that many of the aerosols, you get these very fine droplets. And these very fine droplets are so small that they can just fly through the pore space. And you can't make the mesh tighter because then you can't breathe. So what you actually have to do is you have to have another layer that's water wet that actually attracts the droplets, so the droplets stick essentially to the fibers. So you have alternating, basically plastic fibers and either natural, say, cotton fibers or fibers that have actually been charged so they attract the droplets. Okay, so that's how surgical masks work in principle. At the moment, of course, it's done empirically. The idea is maybe our insights into wettability could help the design. Fuel cells, right, it's the other way around. And as I've already said, you have these carbon fibers, they conduct electricity, so that's great. But some of them, some percentage, you cover in Teflon to create this mixed wet state. What percentage? What coating? Again, it's normally done empirically, and then obviously people are interested in electrochemistry, which is clearly very important. Again, a porous medium look at this may help, okay? May contribute, maybe is a better way of putting it. So actually, I'm going to wrap up here. Hopefully there's plenty of time for questions. So does it matter? Again, as I said, you know, Paul Lab knows it matters, but I think it's very important as a community that we show that flow in porous media really is a scientific discipline in its own right. It's not, oh, he works on oil, he works on CO2, he does something else, and we're sort of in our silos. No, we work on flow in porous media, and it's a really important scientific discipline with a huge range of problems. And in fact, I would say scientifically or societally, absolutely vital. So I'd just like to acknowledge my funding. As I said, we have received generous funding from the oil industry, much of it, I'd have to say, to work on CO2 storage. And I would also, as usual, try and plug my book. But this was written a few years ago, and I used to joke that very soon it will be obsolete. And I think at the moment, to a certain extent, it is. All of the ideas I presented here on minimal surfaces have just come out in the last few years. So I'll finish there. Thank you very much.
Yeah, thank you very much. Thank you very much for that very interesting and refreshing talk. I would propose if there are any questions on Zoom, just raise your hand. And are there any questions here in the audience? Or something on Zoom? Just quickly check. Doesn't look like that. So no questions at the moment, but if there are some questions arising, I would just forward them to you. Yeah, thank you very much again.
You know, that's fine. Yeah, if anyone has any questions, you can certainly use the chat function, or you can email me directly. I'd be more than happy to interact with you. Okay, thank you.
Yeah, thank you and have a nice day.
Okay, thanks very much.
Bye.
Bye.